Okay, we're going to look at another example with a Y connected and a delta connected load on the same circuit. So in this example, we've got three 15 ohm resistors, and they are connected in Y, and we've also got three coils that are connected in delta to the same three-phase 12208 supply. The three coils have an impedance of 20 ohms and a power factor of 0.866. So because they're coils, we know that that is a lagging power factor. So let's go ahead and I'm going to put some values on here. So in this case, all three of these resistors are the same value. They are 15 ohms. So R is equal to 15 ohms. And over here, our coils, all three coils are 20 ohms. And they're at a 0.866 power factor, which works out to a 30-degree lag. Okay, I'm going to go ahead now and start calculating some of the values for the Y circuit. As you know, we're trying to figure out the total current here. So I'm going to use A phase. And so in order to do that, we have to add the line current in Y to the line current in delta at their angles. So let's first start by calculating the line current of the Y. So I phase is equal to the V phase divided by the impedance in each phase, and that in this case it's resistance. So we're going to go with our phase voltage is 120 volts. We're going to divide that by the 15 ohms. That works out to 8 amps. So in Y, I line and I phase are the same value. So line current is also 8 amps. Now where do we plot that? So if we're dealing specifically with A phase, we know we had to change our reference to our line voltage. So that puts our phase voltage down 30 degrees. And that phase current is right in phase with the phase voltage. They're resistors. So since line current and phase current are the same thing, I'm going to go line current IA of the Y is going to be equal to 8 amps, and we have to plot it right at 330 degrees. Okay. Next, let's move on to the delta circuit here. Okay, so we can go ahead and calculate phase current again for the delta, and it's a balanced circuit, so I phase is going to be equal to voltage of the phase divided by the impedance in the phase this time. So this time we have a 208 volt phase voltage. Our impedance is going to be 20 ohms. So that works out to be about 10.4 amps. So I'm just going to pause here for a second. I want to put that on my phasor diagram here. Okay, so over down our phasor diagram, we've got our line voltage or phase voltage. It's the same thing, so that's our V phase. And in this case, we're dealing with a coil. So we have to put our phase current 30 degrees down from our phase voltage. So that would work out to be about right there, 330. So we'd go 360 minus 30, so that 10.4 amps phase current is at 330 degrees. Now this is a balanced circuit, so we can still use our root 3 formula. I line is going to be equal to I phase times root 3. So that works out to 10.4 amps times root 3. It should be about 18.01 amps. So the other thing we can remember, as long as we have a balanced circuit, I line will lag I phase by 30 degrees. So following that rule, I phase occurred right here at 330. We subtract 30 degrees. We have to plot I line at 300. So IA, line current IA of the delta, is equal to 18.01 amps at 300 degrees. Okay, let's go ahead and add this up now. So IA total is going to be equal to IA of the Y at its angle plus IA of the delta at its angle. IA of the Y is 8 amps at 330 plus IA of the delta, 18.01 amps at 300. We put that in our calculator. It should come to about 25.3 amps approximately at roughly negative 50.9 degrees. So negative 50.9 degrees. But we want to express that as a positive value. So 360 minus 50.9, we would say it's at 309.1 degrees. And there's our IA total. So if I put the ammeter here, should read 25.3 amps, and it should be at an angle of 309.1 degrees. Thanks, we'll see you on the next video.